All right, so looking at how much copper you would need, right? If you were trying to actually use the copper, copper does not absorb very much energy for a given temperature change, right? Specific heat capacity is low, 0.3. So it would actually take quite a bit of copper to cool down our mixture. What we're interested in is some more efficient, some better way to do this. Okay? In particular, it would be great if we didn't have to try and keep like a chunk of copper insulated while we brought it up into the mountains. If there was some way that we could have a chemical reaction that we could use to cool down our ice cream mixture, that would probably be a lot more efficient way to go about doing this. So we need to understand how energy works with chemical reactions. How can we model it? How can we calculate it? How can we do all that kind of stuff we want to do with energy now in terms of chemical reactions instead of just touching two things together, which was what we were doing before. We were literally just touching two things together and measuring how their temperatures would change. Now we want to think about, okay, I'm going to have a chemical reaction that's going to take place, which means I'm going to have to worry about stoichiometry, I'm going to have to worry about moles, I'm going to have to do all that fun stuff that we know how to do, and I'm going to add into it energy. I'm going to add into it joules. So we have chemical reactions. We've done this. You have burned magnesium before. We've seen what happens. We get an intense release of energy. Okay? We get a lot of heat. We get a lot of light. There's energy being released. It's an exothermic reaction. Energy is given off. When we want to deal with energy in chemical reactions, we can literally write the energy in. For every 1 mole of magnesium I burn, I will release 601 kilojoules of energy. Half a mole of oxygen. So if I burned 1 mole of magnesium and half a mole of oxygen, if you wanted to, this is not very easy to think about in terms of individual atoms, but we can think about it in terms of moles and it works fine. No, we can use fractions. You really can, just not very common for the introductory stuff. Normally we just say whole numbers. But 1 mole of magnesium reacts with half a mole of oxygen to produce 1 mole of magnesium oxide. You could, of course, double everything on here if you wanted to, including the energy value. It's going to be a per mole value, yeah. So this is kilojoules per mole of magnesium burned, or per mole of oxygen, magnesium oxide formed, or per half a mole of oxygen used up. The coefficients matter, okay? Now, so if I burned 1 mole of magnesium and I collected that, my Q value would be negative 601 kilojoules per mole of magnesium I burned. Okay, so that would be sort of the Q. We can relate the energy change of the reaction, what we call the enthalpy change to the Q value. So enthalpy change in enthalpy. Enthalpy delta H is our heat. That's the heat at constant pressure. So no work involved. We don't have to worry about work. This is just heat. So enthalpy, the change in enthalpy is essentially our change in heat per mole. So the delta H for this reaction would be negative 601.6 kilojoules per mole. And that's our enthalpy value. We call that the enthalpy. We'd say the enthalpy of the reaction, that's a common phrase that we'll hear, and it is essentially the heat, it's like Q, but per mole. Most of the time when we do Q, we're talking about a specific reaction setup. Our enthalpy value is a per mole value. Yep. No, that's the enthalpy for this reaction. Remember, each reaction is going to have its own, it's going to release its own amount of heat. Sometimes it'll be a positive value. It'll be endothermic when it'll absorb energy. Okay? So that's literally exactly what we want. We want to go through and we want to look for a reaction that will absorb heat. Okay? Because we want a chemical reaction that's going to be endothermic. It will absorb heat from the surroundings, and the surroundings we want it to absorb heat from will be our ice cream mixture. So we could arrange a system where it's in a reaction vessel, that then we immerse the reaction vessel in our ice cream mixture, and it will absorb heat from the surroundings, from the ice cream mixture, and freeze it up. So what we want to do is we want to be able to calculate how much heat will a given reaction absorb. Okay? And so we want how much reactants do we need, things like that. We want to be able to calculate the enthalpy change, the delta H, on a per mole value, because that's what we need to go through and actually do our calculations. We need a per mole value so that we can stick it into a stoichiometry calculation, calculate how much reactants do we need, how much products would be made, whatever we want. So we need to be able to convert from a Q value that we can measure in the lab using calorimetry, and that's literally, we're going to measure it using our coffee cup calorimeters. We want to be able to measure the Q and then use that to tell us what is the delta H, what's the enthalpy change per mole. So the reaction that we might think about using is this one. Here's our ethanoic acid, right, our acetic acid bottle. And I'm going to react 100 milliliters of that. I'm going to pour it into my cup, and I'm going to measure the temperature. This time I'm using a digital thermometer. So I can measure the temperature, and the temperature is going to be 20.1 degrees Celsius. So that's the starting point. That's the starting temperature of my ethanoic acid solution. And to that I am going to add some baking soda. Okay? So I'm going to add baking soda, and I'm going to add 8.401 grams of baking soda. I'm going to put that baking soda in there. So those are my two reactants. Okay, those are my two reactants. When I do that reaction, we know that we will produce carbon dioxide, water, and we'll have this sodium acetate left in the solution. The temperature went down. Okay, and this is true. When you react baking soda and vinegar, the temperature actually goes down. It's an endothermic reaction. It absorbs energy from its surroundings. In this case, I had the vinegar reacting with the baking soda, and that absorbed energy from the water. Remember, this reaction is basically all taking place in water. Yeah, you got, sure.
Hi everyone, I'm shocked you asked for this off my class president.
All right. So the temperature went down. This was actually an endothermic reaction. The acetic acid molecules reacted with the baking soda, the sodium bicarbonate, and when they reacted to produce carbon dioxide and water, they absorbed energy from the rest of the solution, from the water in the solution. Our system is really the acetic acid and the baking soda. The water is part of the surroundings. Okay? And we're measuring the temperature of the water. That's what we're measuring the temperature of. So we now have our final temperature. Okay? So we can measure, we can determine how much energy did the water lose. We know the grams of water. We're going to assume that the solution has a density of 1. So we have 100 grams of water, basically. We have the specific heat. We have the temperature change. We can calculate that the energy change for the water is negative 4,807. So that change, that negative 4,807, that is the energy absorbed by the water. Okay? Or excuse me, the energy the water lost, because our reaction was endothermic, it absorbed energy. So we know in these types of problems, right, that the energy that the water lost is equal to the energy that the reaction gained.
So if you didn't have that much energy in its surrounding, would vinegar baking soda not react?
That's an interesting question. I don't know. That's a really odd edge case. You'd have to yeah, if there wasn't enough energy, the reaction essentially wouldn't take place. Yeah, it would be tricky. How would you make it so there wasn't enough energy? You'd have to be like really, really cold, like very low degrees Kelvin. Why chemical reactions take place in the driving force is a different aspect of chemistry, which we will learn about. And there are energy changes involved in that. It's an interesting question.
Speaking of temperature, what happens
273.15.
Sure. But what happens if you're at negative 273.15 degrees Celsius?
You can't get that low. It's not physically possible. The lowest temperature you can get to is infinitesimally close to 0 degrees Kelvin. 0 degrees Kelvin is called absolute zero because it is absolutely the lowest temperature theoretically that you could be at. But you can't actually get there because of quantum mechanics. So yeah, that's the lowest possible temperature is, just a tiny fraction above that. All right, so here's what we do know. Delta H, the change in enthalpy, is going to be the energy of the reaction divided by the moles. Okay? And so moles, when we say divided by moles, typically we want to specify moles of what? In this case, these are all 1 to 1 to 1 ratio, so it doesn't matter. But otherwise, we would have to take into account the stoichiometry, the coefficient of the reaction. Okay? Pick something that is 1, that has a coefficient of 1 generally.
So when we get the energy, like Q from water.
So we got Q.
But do you make it positive? So it's
Yep.
negative. But if it's positive, just keep it
No, we'd make a negative.
Oh.
The negative here means change the sign.
Oh,
Because this is the energy that the water lost, negative value, water lost energy, but the reaction gained that much energy. So that's why the sign changes. So we need to calculate how many moles do we have, okay? And this is an exact stoichiometric mixture. So we used up 0.1 moles of vinegar and 0.1 moles of baking soda. Otherwise, we'd have to figure out which one was the limiting reactant and go with the moles of the limiting reactant. So we're going to take our 4,807 joules. We're going to divide by the number of moles. It's the same either way, 0.1. So we're going to have a delta H value of 48,070 joules per mole, or 48.07 kilojoules per mole. This would be per mole of reaction taking place. Per mole of reaction. They will tell you what they want. Typically, kilojoules per mole is the most common. Okay? Yeah, moles to the negative 1 power is like saying joules over moles. Joules per mole.
Oh, so if you put a slash.
If you put a slash and got rid of the negative 1, that would be the same thing. Right? Because to the negative 1 power means 1 over.
Yeah.
Yeah.
Okay.
That's all it is. It's just an easier way to type it. All right, so now that we have this concept of a value that's per moles, a value that we could literally write in the equation, which for this equation we would put it on the left-hand side. We'd have a plus 48.07 kilojoules over here on the left-hand side because this is endothermic. Endothermic reactions, you see the energy term on the left-hand side as it's a reactant going in. Exothermic, you see the energy term on the right. It's being produced. It's a product. So those are, you can see them in the reactions. Notice this delta H is positive. That's endothermic. A negative delta H would be exothermic.
So in the reaction, you write the Q value and you write the delta enthalpy.
Delta H. Delta H is the way you typically see those written. Because it's a per mole value. And I remember our chemical reaction is all based on mole ratios. So now that we have this delta H value, we can take this equation and we can turn it around. And we can say, hey, I need to absorb a certain amount of energy. I've calculated that value. Okay? I'm going to need to potentially truck in baking soda. I can get vinegar in the mountains. I can make it. Bacteria will eat sugars and produce vinegar. You can do that up in the mountains. We have water. We're growing our sugar beet crop. We can ferment that and produce vinegar, basically. But we will need to, say, bring in baking soda by pack mule. So we're going to want to make sure that we know exactly how much do we need to react to absorb enough energy to cool down our ice cream mixture. So we want to go back and now we want to reverse this. We said, okay, for a batch of ice cream, let's say that we need to remove 26 kilojoules. Okay? Well, kilojoules. Remember, that's kilojoules. So for a batch of ice cream, I need to remove 26 kilojoules. I have the chemical reaction. This is the chemical reaction. We have the delta H. We have the enthalpy value. we want to do stoichiometry. How much baking soda do I need? I start with my given amount. This is like an amount. Okay, this value here is like an amount of reactant or product. This is an amount of reactant that I need. How much baking soda will give me this much energy absorption? I'm going to start with the 26 kilojoules, and I want to convert from kilojoules to moles. Okay? I know that for every 48.07 kilojoules, I need 1 mole of baking soda. Remember, this is 48.07, and this is 1. Okay, this delta H value is per mole. Per mole of reaction means 1 mole of vinegar, 1 mole of baking soda. Those are the reactants that I would need to absorb that much energy. So that's a ratio that I can use to do the conversion. Kilojoules would cancel out, and I'd be left with moles of baking soda. Then I'm back onto solid footing, stuff that we've done tons before. Once I've got moles of baking soda, I can convert that into grams using the molar mass from the periodic table. No, not necessarily. I mean, you can use a solution. That doesn't matter. It's the amount of vinegar that I care about, not necessarily the amount of solution. Yeah, the solution would absorb heat, but then that heat would then be absorbed from the surrounding thing. It would depend on exactly how we do it. But I could, of course, also get pure vinegar, too. I can either buy that or make it.
But if we use baking soda and vinegar to cook on our ice cream, then we have baking soda and vinegar in our ice cream.
Not necessarily. If we would put a container, probably a metal container that would conduct heat really well, have the reaction going inside that and stick that into the middle of the... So they didn't mix, but they could thermally interact. They could be at thermal equilibrium. All right. So we find out that we need 45 grams of baking soda. Should we go through and do this math? We need 45 grams of baking soda. Okay? So remember that this delta H value, which you should write down, it's on the worksheet today? It's on the handouts, isn't it? Okay, good. That value is a per mole value. Per mole of vinegar, per mole of baking soda, per mole of carbon dioxide. These are all 1-to-1-to-1 ratios. But if it wasn't a 1-to-1 ratio, let's say there was a 2 here, how would that change this math? What would I have to change? See, this is per 1 mole. If there was a 2 here, I'd have to put a 2 there. This is just like normal stoichiometry. You use the value from the coefficients. Okay? All right, so I'm going to ask you to do a problem now. I want you to calculate how much heat would be absorbed if 250 milliliters of 1.5 molar ethanoic acid reacted with excess sodium hydrogen carbonate, excess baking soda. So this is not, no limiting, you don't have to worry about a limiting reactant problem yet. We'll get there. You will. Right now, I just want to do a stoichiometry problem. But it's not, I'm not giving you grams, I'm not giving you moles, I'm giving volume and molarity. Volume and molarity. And I'm asking you to go through and do a stoichiometry problem to calculate the energy. Your final answer should be in kilojoules. Ethanoic. Yeah, there's an N missing there, isn't there? Ethanoic. Yeah, that's a missing N. All right. Anyway, give it a shot. Go through, do this calculation. There's a box on the back of the page. You have the delta H for this reaction. You have the balanced chemical reaction. Go ahead and do this calculation. All right, so let's go ahead and take a look at this. Step 1, did you calculate the moles of ethanoic acid? Yes. Volume times molarity would give us moles. Remember, molarity is moles divided by volume, so I move the volume to the other side. Equations on the useful equation sheet. Right, molarity is equal to moles over volume. When I multiply those, I get the moles of ethanoic acid. Now I need to take my moles of ethanoic acid and I need to convert from moles of ethanoic acid into kilojoules of energy. And that's what the delta H gives me. That's the ratio between the moles for my balanced chemical equation to kilojoules of energy. You have the equation, it's a 1, the coefficient on the ethanoic acid is 1, that's why there's a 1 here. And then 48.07, that was the value of delta H that we found from doing the calorimetry. We did it in the coffee cup and we measured the temperature and we calculated delta H. Okay? But now that we have delta H, we don't have to go and run every kind of experiment with every different mass, with every different number of moles. We can use the delta H as a ratio, just like we would when we're doing any kind of stoichiometry. So we get a value of 18 kilojoules would be released, or absorbed, I should say. This is an endothermic reaction, 18 kilojoules. Questions about this? This is an endothermic reaction. If you were to write it in, you would put it on the left. Plus 48. In the balanced chemical equation, you're going to use a delta H value because it's a per mole value. This is the value if you use this amount of stuff. That's why there's no per mole here. Okay? That's how much heat would be absorbed, 18.0 kilojoules. Now, this is an important thing, okay? Notice this one is positive because it is energy that's being absorbed. But if you were to calculate this in terms of an exothermic reaction, your value would typically come out negative because your delta H would be a negative value. But you should never say that, say, negative 20 kilojoules were released. You can't have negative energy. It doesn't make sense except in some really weird quantum mechanical situations. Okay? So you don't say negative energy released. You say energy released. The negative is what means the released part. You could say delta H is equal to negative 20, but you wouldn't say negative 20 kilojoules released. You just say 20 kilojoules released. Delta H is negative 20. Okay? I don't want to see anybody writing negative energy released. That's bad news. I probably shouldn't have said it so many times. Now you're all going to write it. Don't do that. All right, that's it for today. Just that one little piece. We will expand upon this on Thursday. Tomorrow we're doing the lab. Tomorrow we're actually going to do some of this calorimetry stuff with the coffee cups and the whole 9 yards. No, we'll do it during this second period. Tomorrow morning during zero period we will be going over homework problems. Next week on Friday. Friday before winter break.